Hello and welcome to another video. In this video, we're going to be working on a number of subarrays that match a pattern 2, and this can also be solved for the first version of this problem with the easier constraints. So so this is going to be the last problem of the weekly contest 384, and let's get into it. So here we have a 0-index integer array nums of size n and a 0-index integer array pattern of size m consisting of integers -1, 0, and 1. Subarray of size m plus 1 is said to match the pattern of the following. This is a little bit confusing, so let's just go over what they actually mean. So let's go through the examples and then we can see exactly what they mean. So essentially when you have a pattern 1, 1, 1 means the current element needs to be bigger than the one before. So for a pattern 1, 1, you need to have an array of 3 elements. So if a pattern is 2, you're looking for 3. If a pattern is 3, you're looking for 4. And this is the pattern you're looking for. So you're looking for one element to be bigger than the one before, and then the next element to be bigger than that. So essentially something like 1, 2, 3 would work here because this pattern would hold because 2 is bigger than 1 and 3 is bigger than 2. So this kind of array would give you your result. And that's kind of what they show you here. So any 3 elements that hold that is true. So like 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6. Now in the second example, you're looking for 1, 0, -1, which means you need an element that's bigger than the one before. Then you need an element that's equal to the one before. And then you need an element that's smaller than the one before. So these two would work because here 4 is bigger than the one before. This 4 is equal to the 4, right? So this 4, 4, 1 would be represented like this. This 4 is bigger than the one before. The second 4 is equal to the previous 4, which is 0. And then -1 means the element after that is smaller. So you're looking for this pattern. And also 3, 5, 5, 3 works. So essentially for this problem, all you're concerned about for your numbers are, is it bigger than the one before? Is it smaller or is it equal? So you don't really care what the numbers are. You're just looking for comparisons. So let's actually make an array here. Let's copy these numbers and then let's use them. So let's say we have some array and our numbers will be these numbers. So let's say we have 1, 4, 4, 1, 3, 5, 5, 3. So for this array, let's just move this down here. And then the pattern we're looking for is 1, 0, 1. So we can have that as well. And let's use an array for that as well. Let's get rid of all the unnecessary things. Let's make this a little bigger, kind of to fit, close enough. So the pattern we're looking for is 1, 0, 1. So like I said, we don't really care what our elements are, just the relationship to the previous element. So in fact, what we can even do is we can rewrite our element. Instead of having an element, we'll just rewrite it based on its relationship to its previous element. So if it's bigger, so the pattern we're looking for is -1 here. So let me put this here. So this should be -1. Okay, so for every element, like I said, we only care about if it's bigger or less than or equal to the previous element. And that's how we build the pattern. So for 1, it's not going to be like there is no previous element. So we're just going to leave that value. But for the rest of it, we can rewrite it, right? So this 4 is bigger than 1. So if the 4 is bigger than the 1, actually what we can do, let's actually do it like this. It'll be a little bit easier. So let's make an array down here just for these extra elements. So here we go. We don't need any of these. So what we're going to do is we are going to, for all these elements other than the 1, we're just going to write down what's the relationship compared to the one before. So this 4 is bigger than the 1, so we're going to have a 1. This 4 is equal, so we're going to have a 0. This 1 is less, so -1. This 3 is bigger, so 1. This is bigger, so 1. This is equal, and this is less. So these are our patterns, right? We don't really care about this array, we just care about this pattern. And now we're basically asked, given these patterns, do we have this one and where is it? So we have it here. So if you actually look, this is the array, right? So 4, 4, 1. and you include the element before those. So it's 1441, which is this pattern here, right? Now, if we look again, it also occurs over here, which is 553. And so it includes these three elements plus the one before. So you can see, like, basically you can take your array of numbers and just for every number other than the first one, just write 1 if it's bigger than the one before, 0 if it's equal, -1 if it's less. Then once you do that, you basically have a pattern matching problem. So you're asked, like, given an array of numbers like this and an array of numbers like this, how many total matches are there, right? And what does that look like? That looks very similar to a string comparison, right? Like, imagine if these were letters. Like, if I just say, okay, let's make the 1 an A, 0 a B, and a -1 a C. Now you're basically asked, given a string, how many times does a substring occur, right? So given a string, how many times does a substring occur in a string? And so if you've seen some other contest problems, this is basically just, there's two ways of doing this that are common, either KMP or a rolling hash. And I'm going to use the rolling hash because that's what I'm most familiar with. So essentially, you need to do a couple things for the rolling hash. So first of all, for your actual pattern, so this pattern, let's have these indices be one indexed. What you can do for this pattern is you can turn this into a hash value. Pretty easy. You can just use a basic hash function where you just take, and actually I tested this with, you can actually just use the 1, the 0, and the -1, and that's totally fine. Normally you'd use like the ASCII value of the letter, but you can actually use these and it still worked out. So you just take the value in the cell times the, so you can take a prime number here. So prime, I actually tested it with something small and it worked. So I tested it with like 7, but like a good hash function wants to have like a bigger prime number because essentially you want to make sure that you don't have like false positive collisions. So a typical one that's pretty common is like 31 or 131. I use 7, so even 7 worked. But like I said, if you want to be safer about it, just use something bigger like this. So you take your value here times a prime number like one of these to the index. And this is going to be a one index. I believe 0 index works as well. So essentially for like this pattern, we would say like, okay, 1 times, let's say we use 31 as our value, 31 to the 1 plus, so this is going to be 0 plus -1 times 31 cubed. You get that, and then you get this whole value. And because this pattern can be really long and nums can be really long, you can just mod it by 10 to the 9 plus 7 to get an actual value to keep this like in bounds. So you mod it by 10 to the 9 plus 7, you get some value here, right? You get some hash value. And then once you do that, let's say we're comparing it to this. Like we don't need this anymore. So let's get rid of that. Here's our actual values for our string, or not our string, our numbers that we converted to. So this is going to be like index 1, 2, 3, 4, 5, 6, 7. Then there's a couple of ways you could do this, and I opted for the harder way to get an O1 space solution, which actually worked, but it was a huge pain. So the way you can do this, that's the huge pain way, is you have a 2-pointer. So for example, you have a 2-pointer. So basically, like, let's say, let me move this down here. When we compare this, like once we get this hash value, we're essentially trying to compare like, okay, is this equal? Is this equal? Is this equal? Is this equal? And we have to do these all in O of 1. So for this to be equal, we basically have to get the hash value for this section here. And the way to do that in O of 1 is you kind of do the same thing as I did up here. You do the same thing for this, right? So you just compute the value for this, the value for this, the value for this. You add them up and you have 2 pointers, and your pointers will be a prefix sum basically. So what you do is you start over here, you add up all your values, and then you get some total hash value here, and you say, are they the same? And if these two are the same, then these are equal. Now here the indices line up, right? Like this is 1, 2, 3, and this is 1, 2, 3. So let me actually move this down here and write the indices. So here the indices line up because, and this is important because we use the indices to get the hash value, right? And remember, it's the value times a prime number to this index. So here the indices line up. So if the values are the same, they'll be equal. And basically what you do is you compute a cumulative total here and a cumulative total here. So here there's nothing yet, but I'll kind of show you how this is going to go. So here they're going to be equal. So you just put 1 in the result. But now the problem is now you have to do this comparison. And this is like where it gets annoying with an O of 1 solution. So you can compute up to here, but now you had to have subtracted this value here. So that's why you need to like compute these values as you go, and you need to maintain a 2-pointer window. And this is going to represent the total up to here, and this is going to represent the total up to here. And if you want to compare this chunk to this chunk, then you just do this right hash minus this left hash. And you can just keep track of the value. So like as you go right, you will just keep adding your current thing. And as the left moves over to make your window, to keep your window the same size, so you have this being your actual hash, you can just keep adding over here as well. And the other annoying thing is you need to get powers of whatever you pick in O of 1 as well. So I actually got variables for that, but we'll talk about that in the code. But essentially, that's one way to do it. The easier way to do it is just pre-compute a prefix sum, pre-compute this whole prefix sum, and then you'll have an O of n solution, and pre-compute powers of 31. And then it's a lot easier. So then, like if you don't, and I'll show you how to do that. But basically, then what you can do is no matter where this is, you can just figure out like, okay, where's the index that matches up? It's right over here. And what's the part I have to subtract from? It's right over here. And if it's all pre-computed, it's a lot cleaner, but it's going to be O of n space. So anyway, so here the indices don't line up. So you can't just like take this value and compare to this value, because this value at the top, remember for every single number, it's value times some prime number, let's call that p to the index. Well, this is a value times the prime number to the 2 to the 3 to the 4, and this is 1, 2, 3. They don't line up. So to make them line up, I also talked about this in a previous function or in a previous problem. You basically need to figure out like how far apart these two things are. So these two things are 1 apart. So you need to multiply all of this by that prime number. So if you multiply all of this by that prime number, because they're only 1 apart, then this 1 will turn into a 2, this 2 will turn into a 3, and this 3 will turn into a 4. And that will make it line up. And that's like part of the hash function that you need to do to compare things to make them line up. So these won't be equal because you can see like the values are different. Then essentially we do the same thing. And then remember, this whole thing is pre-computed. This is just one value that we get up here, this hash value. Then you move it over here, you do the same thing. Now they're 2 apart, so you take this value, multiply by p squared, but these values are different, so this is not going to line up. So then you move it over here, these values are different, and you need to multiply it by p cubed now. And then finally over here, these will be the same, and you need to multiply by p to the 4th to make it line up. And that's kind of the idea. You just do a rolling hash, or you learn KMP. You basically have to learn a string comparison function that gives you O of 1 string comparison to do this. But once you recognize that like you don't really care about your numbers, all you care about is this pattern, you can just change your numbers into the pattern. And look, now your problem is basically just find how many times a substring occurs in a string. And we've done like a few LeetCode contest problems doing that now. For some reason, they like to show them all the time. So yeah, so let's take a look at the code. It's a little bit messy because, like I said, I made it a 2-pointer where if you want to make it easier, you can pre-compute a prefix sum and pre-compute powers of whatever number you have. So what I did was, first of all, I got the pattern hash value for my pattern. And as I was going through it, the other thing is you need to, like I said, you need to have powers of 7 and O of 1. So I was just, as I was going through every single index in my pattern, I would just multiply my power of 7 times 7. So I can get those in O of 1. The cleaner way, if you want to have an O of n solution, just pre-compute powers of 7 all the way up to the length of nums, and then access them later. and then I had a left pointer and a right pointer, and then I basically went through my numbers and I updated my pointers. So my value was 0 if the numbers are equal, 1 if the number is greater than the one before, or -1. And I got my current hash value, which is just the value times, like I said, this is also messy. I had to keep track of a right power and a left power of 7 because I wanted to get those in O of 1 and I wanted to use O of 1 space, but probably not worth it. Like I said, better off just pre-computing all powers of 7 or whatever number you use here, 31, 131. You just pre-compute that all the way up to the length of nums. Be a lot cleaner, and also pre-compute a prefix hash of your nums all the way up to the end, and then just go through the indices. So then I basically also had to check if my if my index is long enough to start matching the pattern, right? So if the pattern is length 3 and my word starts at index 0, basically in order for this to match the pattern, I have to be at index 3 or greater. So if I'm at index 3 or greater, then I have enough to match the pattern. If not, I can't match the pattern yet because it's not long enough, right? Like if I'm over here, I'm not going to match the pattern. So, and if I do match if I am trying to match the pattern, like I said, I need to make sure that my window is always 3 characters. So after I try to match it, I move my left pointer up and I subtract the old value. So basically, I subtract this value here, whatever this hash was. So now I can get like this hash for the next part. So you just keep subtracting like over here, so keep subtracting over here. So you are always maintaining a hash value that's the same length as this. And finally, once I do that, then the other part, like I said, you want to make them, because the indices don't line up, you want to figure out like what to multiply your number by. And that's what I did here. So I just multiplied my number by the left power to make the indices line up, because this starts at like 1, 2, 3, let's say, and this can be wherever you are, right? So you just figure out what number to use to make that line up, and then do that here. And then if your numbers are, let me see where I did that. Right over here, right? So I take my window hash, and I take the pattern hash plus or multiplied by the power I need to multiply to make the indices line up. If they're equal, then there's a pattern match. So that part is just literally basic. Like once you get that this pattern, you have to match a pattern to like an overall array. It's literally just find the needle in a haystack. How many times does it occur? It boils down to that problem, which, like I said, is literally just basically KMP or a rolling hash, whatever you're comfortable with. I'm probably going to end up learning or like restudying KMP because this is a little messy. I think KMP is a little bit cleaner. Also, KMP has better runtime. So, but I did manage to make this in O of 1 space, but it was kind of a pain. So yeah, so this is going to be time O of n space O of 1, and we can submit it and show. Is this the right problem? Yeah. And here you go. And like I said, I think the KMP has better runtime, so yeah. And yeah, that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And you can literally take the solution and post it in this problem over here, like literally copy paste, and it runs fine because it's basically the same problem. So like I said, kind of messy. Definitely would recommend, especially if you've never done the rolling hash, would recommend just pre-computing a prefix sum and a power and using that. And yeah, it's going to be all for this one. So if you did like this video, please like it, and please subscribe to the channel. So thanks for watching.